Hello, I'm Graeme Lubbe, and I'm from Group 8 with Tinashe Chinyati. And our project for MIT808 was forecasting COVID-19 through stateful LSTM. So the goals of our project was to develop SIR models on South African data that incorporate vaccination data. Um, this is basically to compare such SIR models with models that do not incorporate vaccination data and then verify the effectiveness of vaccination. It was also to identify and develop additional models to be used on the same data that may be used to forecast COVID-19 cases in the future. So early challenges that were encountered in the project was simple soil models, even when extended to be a bit more complex, do not fit well to COVID-19 data. One workaround on this is to use segmented models, which basically fits a certain model on each wave. So you split your data and fit a certain model on that, which would be useful in evaluating the each wave and the effectiveness of measures placed by the government during these waves. But that does not improve the ability to forecast in the future. Okay, so basically how the SIR models work is that they take the entire population and places them in a group, which may include the susceptible, infected, or recovered group, and then these groups change based on your infectivity rate and your recovery rate. And what we added to this data is that the recovered group may return back to the susceptible group through a parameter called weighting immunity, and also that the population may grow through the birth rate, and that some of the population is removed through the mortality rate. So early indications show that there is a possibility that it might predict multiple waves if fit well. This was basically just on random parameters, but the second that the model was fit to actual data with black box optimization, it's clear that it does not fit extremely well to the actual data, and with only a single wave predicted on the what was actually the third wave. So just an introduction to stateful LSTMs. So LSTMs are a form of recurrent neural network that negates the vanishing gradient problem on standard, that is typically found on standard recurrent neural RNNs. It does this by basically using a sliding window and adding more weight to more recent data that is in that window. So a stateful LSTM maintains the time between the dependency between a variable and its lag variable by not shuffling samples during training. So the such models are typically useful for data that are autocorrelated over time. So the methodology that was used, so we used the daily COVID-19 cases as reported by the NICD. And for this model, we used a lag of 170 days, which we determined by investigating the autocorrelation at different lags. So if you look here, the autocorrelation at 170 days is close to its peak. The actual peak is closer to 174. And the ACF value is 0.54 at this point, which is actually considered quite good for autocorrelation for time series data. And so we used a batch size of 29, which divides evenly through the 170 and trained on 70 epochs. Okay, so the structure of the network contained an input layer with the lagged cases as input, 2 hidden layers, and a dense layer, a dense output layer. The model is tested through a backtesting strategy with a split of 340 and 170 for the training test datasets. and 29-day skip for each new subset. So this resulted in 11 subsets that were used to evaluate for cross-validation. The epochs that were chosen, mentioned earlier, were chosen to prevent overfitting on any of the subsets. So first, what you can see on the cross-validation, on the first few slices, the model actually predicts the wave quite well, and the root mean square error between slice 1 and slice 6 varies between 3,300 and 4,400. But the second that we move to slice 7, where the information from the first wave is lost, the root mean square error increases significantly from 8,000 and increases from there to slice 11, so which is the latest COVID-19 data, to 17,000. So what we can see from this is basically that the model fits well to early COVID-19 data, but as the pandemic is progressing and the shape of the pandemic changes, this predictability is becoming worse and worse. So then finally, here is the forecasting. So as you can see, this is the current data that is available.